Hi, I'm Oliver Gao. I'm the director of Cornell Systems Engineering Program, and we have been doing this what I call systems conversations with our prestigious speakers in our Ezra Systems Seminar Series. Today, I'm very delighted and honored to have Professor Jay Lee with us. Dr. Lee he's currently a professor and also serving as the Associate Vice President of International Office and also director of the Saudi Aramco CO2 Management Center at KAIST. KAIST basically means, I believe, Korea Advanced Science,
Korea
Advanced Institute of Science and Technology. So
Exactly.
It's great to have you here. I do have a very long
Pleasure.
bio here for you, but I think I will leave it to Dr. Lee to talk about himself and also his research in general. Welcome.
Thank you for having me here. So basically, I did my PhD at Caltech, and my PhD was about robust control. So it was in control field.
That's quite away from like chemical and biomolecular, sounds like.
Yeah. So it was very much theoretical work,
Uh-huh.
and about using. Well, back then there was a new technology called model predictive control.
Yes.
And so I worked on taking this model predictive control and interpreting it in the way that we can understand from the classical control standpoint, as well as expanding its scope
Yes.
and addressing things like the uncertainties and so on. So that was my PhD thesis. After Caltech, I immediately started my faculty position at Auburn University, where I spent 7.5 years. And there I continued to work on model predictive control, but there model predictive control was something that started in refineries for multivariable control, constraint control, continuous processes. So I took this and then extended to other types of processes like batch processes, those processes that need to be dynamically operated, like the pressure swing adsorption or simulated moving beds. What else did I do? I looked at the estimation aspects. So I took this idea of optimization-based control and then applied it to optimization-based estimation. We call it moving horizon estimation. So I did a lot of extension and pushing the boundaries of optimization-based control at Auburn. And then 1998 actually, I got an offer from Purdue University. So I moved to Purdue University and spent, I planned on spending a lot more time at Purdue, but I ended up only 2 years, for 2 years. And there I got exposed to a lot more systems issues beyond process control, so such as scheduling and supply chain and so on. Okay, so that was a very good eye-opening kind of thing that there are a lot more than just process control in the systems community.
That's true.
And I started looking at everything as kind of a decision-making process rather than feedback control. Okay, so decision-making in the sense that you have to make decisions in sequence. It's a sequential decision-making, multi-stage decision-making. You have uncertainties and you have continuous inflow of information.
It's like the pathway.
Yeah, so it's that's what control is. You have measurements coming in. You have in digital control you have sample time where you are deciding on the control actions, and you have to continue to do it. And so I started looking at all these systems problems like that from the optimal decision making viewpoint. And then year 2000. Georgia Tech approached me and asked me to
Stole you away from Purdue.
take a position. Yeah, and the reason why I moved to Georgia Tech, besides the family issues and so on, is Georgia Tech had a great industrial and systems engineering school, and they had many good people in logistics and optimization and so on. So that's where I started actually looking at, I didn't call it reinforcement learning at the time. I called it approximate dynamic programming, but it's essentially same thing. Reinforcement learning, you're trying to solve these sequential decision problems in approximate way. And so you can call it approximate dynamic programming, you can call it reinforcement learning. Perhaps reinforcement learning has slightly bigger kind of scope, but essentially same thing. So that's what I worked on. And the reason why I worked on it is when I looked at the existing framework of mathematical programming based decision making or optimization, I found that it was very difficult to address the issue of uncertainty, say stochastic uncertainties. Because if you took the stochastic programming route, it would, in the context of sequential decision making, the bench will grow so fast, the computation will get unwieldy. Okay, and the way model predictive control was doing it was ignoring this uncertainty, and then it was getting feedback and then making corrections. So it's kind of fixing it up afterwards rather than addressing uncertainty from the start. So the only real way of solving this problem was using stochastic dynamic programming, in my opinion. Okay, and so that's what I started working on, and because you couldn't solve stochastic dynamic programming exactly, that I started looking at the concept of approximate dynamic programming, which has relationship with related to reinforcement learning, what they call it.
Also relate like in optical learning.
Yeah, so it's interesting. I started this in like year 2000. Back then, not too many people paid attention to reinforcement learning. Not like today, because of AlphaGo and so on, that everybody's interested in reinforcement learning. But back then, not that many people. But I knew that was the right kind of approach to a lot of these stochastic decision problems.
So actually, that's actually a very good point, because I think, there are good researchers. They can always catch up. Oh, this thing is becoming hot, and they can quickly catch up and do something good. But I think like great researchers, how you can stay ahead of curve, right? Like you said that you started doing that back in 2000.
Yeah.
And then now things are picking up the momentum, which means that I think it's kind of visionary researchers. You can see where things and what is the future need.
So it's probably a little bit ahead of time, because the amount of data available or computation capability wasn't like today. Today we have GPU and big data and so on that you can utilize. So these are much more practical. But anyways, I worked on it anyways because I saw that as the right approach to the problems, and applied it to not only control but scheduling, project management, resource constraint project management, supply chain decisions, and things like that. So my research became much more diverse in scope.
Yeah, so that's of course reminds me like some senior faculty once made a statement saying like before we were tenured, we focus on we are specialists. We focus on tiny things and dig deeper. And after you're tenured, after you become more and more senior, you really become a systems engineer, your research. So you mentioned this, your progress from the early stage of your research, for example, from feedback control, predictive control, and then all the way now to this reinforced learning, this whole process. So, of course, I believe that some real-world applications kind of motivated you because you see the needs, and then you direct your research to those directions. So along the way that you have come from all the way from the start to this point, what are some kind of key challenges, real-world challenges that motivated you to get here? And even if you since you're now talking about uncertainty in the future, so how do you project your future research based on what have you done? So kind of put it in a trajectory, in the sense of trajectory. How would you describe some kind of the key motivating real world system challenges that changed your research direction before and that will keep shaping your research in the future?
Yeah, like you said, when you're young, out of graduate school and so on, you tend to have narrow vision and you focus on it, and I think that's tremendous. But as you grow older, that in some sense you become wiser, and you are more, you develop more broad-based view of things, and can put things in better perspective. And you can start saying things like, oh, this is going to make a difference or make impact in real world or real industrial practice, or this is just going to be an exercise on your own. And so, I think the real world problems were much more complex, had much higher complexity than the kinds of problems that I worked on early. And I knew it had a lot more stochastic variations and things like that we couldn't model fundamentally. And so we had to really get those from the data.
That's right.
Right.
Yeah.
So I think that's the challenge now. I mean, people talk about big data, people talk about learning, people talk about optimization, how to put all this together so that you can take real world problems, okay, based on what's available, which may be data and which may be good hardware optimization package and so on, and then put it all together to solve real problems.
At least for now, like your research interest has a lot to do with this reinforced learning. So from your perspective, what are some of the key strengths and power of this reinforced learning? And I know that you have been, the applicator domain mostly has been like in the energy sector. So what do you see as some key strengths of reinforcement learning to addressing the energy challenges that we're facing today?
So I think, especially when you try to integrate renewable energy into the picture, that you gotta consider, you gotta deal with very different time scales. For example, wind energy, wind speed may change on less than minute time scale. And then you're talking about managing energy capacity over several decades, and they are not independent, okay? Because the way the wind blows, you can't just take average and say, this is how much the wind energy will be added, because wind blowing at 10 meter per second versus fluctuating a lot between 0 and 20 would be entirely different from the energy standpoint.
That's right.
So you have to, the challenge here is that you are dealing with very different time scale stochastic phenomena. And you have to make decisions considering without, kind of coarse graining and things like that. And reinforcement learning, because it's based on data, and you can take lots and lots of data, that it to me it's just the only way that you can address this very different multiple time scale phenomena and make reasonable decisions without making undue approximations.
Am I right by summarizing that actually one of the key strengths for reinforcement learning is really taking the real-time or historical data so that your decision can be made more adaptive, so that you can better address uncertainty and stochasticity?
Well said. Well said. Yes.
I see.
Yeah.
So with that, I saw that you also been directing this Saudi Aramco-KAIST Management Center. Would you like to talk a little bit more about that?
Yeah. So I think systems engineering is a wonderful thing, because nowadays we are asked to address societal problems. And most societal challenges are very, there's no single magic bullet. Okay, let's take CO2 or climate change problem. There isn't gonna be a material or catalyst or some magic bullet which will solve this problem. So you're gonna have to take a little bit of here, a little bit from there, and so on, and really make it into a whole solution. And systems engineer are people who can do this. Okay, I mean it's like the Apollo project, right? That's right. The final mission was to land man in the moon and return him safely to the Earth. Yes. Okay, and in order to do that, various things had to be developed: new materials, new communication system, new control systems, navigation, etc., etc. Right? So same thing with, I think, climate control. That you will need new catalysts, new processes, new solvents, new storage devices, and those will have to be coordinated, and those will have to be packaged, so that we achieve what we're after, which is saving this Earth.
I see.
Yeah, so I think it's a perfect problem for systems engineers to take charge. The way I think of systems engineer is like a chef. Okay, so systems engineer is a chef. He has to be creative, and you get all these ingredients from basic sciences.
Yes.
That you can use, and you get all these cooking equipment and so on, tools from various people, electrical engineers, mechanical engineers, and so on. Okay, yes. And then you got to use them and mix things correctly, so that you produce right kind of foods that will please people, right?
Jay, I really like this analogy. I think this is great. This chef versus a system engineer. I think I like the idea a lot. Especially I think when I was actually looking at your website, you have this lens laboratory for energy systems engineering. Yeah. When I was looking, I really like kind of the three legs of the lens laboratory. You look at energy technology. However, you don't limit yourself to technology, but you also look at efficiency improvement, and later on you also look at systems and policies. I feel this is really kind of a very good reflection of what you just said about how we deal with this. I would love to hear more about you talking about the lens laboratory and your philosophy, and also the specific works you're doing.
Those things seemingly very disparate actually have to be, they very much affect each other, right?
Yes.
Technology development, efficiency improvement, and policies, especially when it gets to energy solutions and the environmental solutions and so on. Okay, without right regulations, policies, certain technologies we develop don't make sense. Okay, so all those have to be combined in the very, very careful and design way, so that the things will work together in harmony. Okay,
yes.
So maybe what I'm trying to do is ambitious, but at least I want to kind of demonstrate how these things interplay, and give solutions, working solutions, at least for problems that are of realistic size.
Yes. So in that case, maybe I think we can take this opportunity to dive a little bit deeper into your lens program as kind of, so because I feel like you mentioned, maybe you could be ambitious, but I think that's a good thing, because people have to be ambitious to accomplish, to address the key challenges. So in your energy lab, so what kind of key issues that your lab is helping Korea in the nation to address, and what things you have achieved, and especially, did you come across any kind of barriers or difficulty in moving forward with your research agenda?
Well, one thing that we are doing right now is there are a lot of technologies being developed for carbon sequestration or carbon capture and conversion. And because there are so many possible products, and even for same product, there are different routes,
Yes.
different catalysts, and so on and so on. So which one is going to be winner at the end, or which ones will be winners? Okay, so even though you don't have the full information because they are still at nascent stage, low TRL, so to speak, that is still very useful to make some sort of evaluations and say that these are the promising ones, that's the one that you should put more resource into. Okay, so we have this kind of a map, network map, which will start from carbon dioxide from various sources, various industrial sources, right?
Yes.
Refinery or hydrogen plant or steel plant and so on. And then we look at all kinds of products that we can make. We put in all sorts of capture processes, conversion processes, and so on. And then we create what's called superstructure, which has everything,
Yes.
every possibility. And then we can evaluate in terms of economics and in terms of how much CO2 reduction we can get. A lot of times, these things end up producing more CO2 than they are reducing.
Exactly.
Yeah. If you don't properly account for it, just because you are consuming CO2 in your process doesn't mean that you are reducing CO2, because you are also using a lot of energy and high energy materials and so on, which may have CO2 footprints.
Absolutely.
Okay, so we created this program that can evaluate these different pathways and different products and so on quickly in terms of economics and CO2 footprint. And then not only you can evaluate whatever path, but you can also optimize. You can set your objective functions, you can set constraints, and then you can have the program find the best ones. Okay.
I see.
And things like that. So then, that serves as a guidance in terms of future technology development. And then you can say things like also, in order for these technologies to be actually implemented, government has to adjust their, tax incentives or CO2 tax in such a way, and you can set your emission target to this, and you may be able to meet that, and so on. So there's an interplay between what the government will do versus what technologies will be developed.
That sounds a very powerful tool. And also kind of you made this superstructure. Suddenly you do have like multi-scale kind of, I think, kind of granularity. So with this kind of powerful tool that you have built, and apparently you have done a lot of research. So now if you jump out of all these kind of technical details, as I believe you also probably advise the correct government in terms of strategy. So at a higher level, what would be some kind of like top 3 policy recommendations or technology development recommendations that you would say to the government or to the decision makers?
One thing I would say is that you can't just ignore this. Okay, so it's not something that you see the problem happening and then do something about it, because it may be too late. There's significant dynamics involved that you have to take preemptive action rather than reactive response. Okay. The second thing is that you have to work with this sort of quantitative evaluations and analysis to come up with the right kinds of policies. You can't just do this politically based on which party you are at or who your supporters and so on. You have to do honest, quantitative, objective analysis to come up with the right policies. Okay, I don't know what the right policies are. I can't tell you because a lot of the model we have is incomplete, in some sense. We still need a lot more data. So that's another thing that I would say, that make those data available, work with people, and help collect the right kinds of data and so on.
Yeah, that's again that's really also like a systems project, right? Like Apollo project.
And there's not gonna be single magic bullet. I'm very sure about this.
Yeah. So speaking of that, in a system and a lot of time, it's really, as you mentioned, it's cross-disciplinary, it's cross-sector. So maybe I think this is a good time for us to maybe learn more about, the institution that you are now serving, the KAIST. So, especially as a social vice president for international office, I assume you also collaborate very closely with international organizations. We would like to learn more about KAIST and your international collaboration, and also, are there any kind of system engineering effort within KAIST or in Korea in pushing forward, like the vision that you have?
Well, KAIST is a very special institution which was created in 1971 at the time of economic hardship in Korea, and it was created specifically to help Korean economy to develop, to industrialize. And it was created as a special institution, not just another university, because it was put under the Ministry of Science and Technology, not Ministry of Education. And it was given also special privileges and so on, military exemption. The students got military exemptions, for example.
I see.
And so it started out as a very mission-oriented kind of university that had innovation at the core. Okay, so I think that has kind of carried through, and innovation is very important for us. And we understand that diversity and interdisciplinarity and so on are very important for innovation. So KAIST created this KAIST Institute, which is which is independent from any academic units we have. We have departments and colleges and so on, but we have KAIST Institute. And there are 6 institutes within this KAIST Institute addressing things like nanotechnology materials, healthcare, bio, artificial intelligence.
Sounds very cross-cutting.
Yeah.
Very cross-cutting.
So
yeah.
That's when we become KAIST faculty member, we can sign up to become a member of faculty of these institutes. And as a matter of fact, Saudi Aramco-KAIST CO2 Management Center belongs to this institute, KAIST Institute.
I see.
So it's meant to be an interdisciplinary center. Yeah.
I see.
With material engineers, chemists, mechanical engineers, chemical engineers all participating. Yeah.
So what is the major mission for this Aramco-KAIST CO2 Management Center? Is that mainly for carbon sequestration, or what are the major?
I think even though it's sponsored by Saudi Aramco, the mission is not to make money for Aramco. I think the mission is to help solve the climate change problem.
Yes.
Okay, and I think in some sense Aramco has taken on a very noble kind of action because they feel that being the world's leading fossil fuel provider, that they had to do something.
Yes.
Okay, so
yes. So for that, and so you mentioned that one key feature of KAIST is actually innovation. So in that case, I'd assume that the education mechanism, the discipline setup, for example, might be different from the traditional university like Seoul National University. So what are some key features? So how does the institute do to implement this innovation mission?
So one thing that's different for us is that most Korean universities, as you admit it, you decide on major. We admit students without major, and after first year, they can decide on their major. And they're not limited in any way. So, chemical engineering, for example, could end up with 200 students one year and 20 students next year. Of course, it doesn't fluctuate that they're large. But anyways, that's the idea. And then this year we've created what's called major without major, so to speak.
Oh.
So they're not attached to any particular traditional discipline, but they will learn,
Create their own curriculum.
key basics of different basic science and so on, and learn to integrate this.
I see.
Okay, so that's something new we are doing. Of course, we have education 4.0, flipped learning. We have Coursera, and we have also so video-based learning and so on.
Yeah. So at Cornell engineering, we have a degree we call independent major.
Yeah.
So like basically as a student, you can identify an advisor and you can design your own program of study.
Yeah. So this is kind of that idea, but we feel that in the future we will need more people who can integrate different knowledge from different disciplines. Okay, so we need the kind of a breadth person as well as depth person.
Yes. So that's why we call system engineer, we always call this T-shaped knowledge structure,
exactly,
right? They're equipped with both.
Exactly.
So I think we're getting towards the end of this due to the time limit. But I would be interested in knowing, like, given all the education effort, research effort, and also I think consulting for the government, all this you have had a very successful career so far. And then what's next?
What's next? Well, I think even though I've studied some good things, I don't think they have materialized. So really make sure that I follow through and make some impact at the end. Whether your technologies get translated into real practice, or whether your recommendations get adopted by they get noticed by government and influence their policies, whether you educate students who can do much greater things than you can. But really focus on making impact. Do things that count.
Already done.
Okay.
Yes. But I think this is really great because I feel as academics a lot of time, especially for junior faculty, their effort a lot of time is directly towards publication, journal papers, top journal papers. So, but from time to time, people they could lose exactly the eyesight that you just mentioned. Like, why do we do research? And in the end, we want to have impact. Right, so I think that's actually very, very. You mentioned earlier, like people become wise. I think that's a very good reflection.
I know all of us.
Wisdom.
I know all of us work very hard, faculty members, and if you're gonna work that hard, you might as well do something that will make impact.
That's right. I think that's the ultimate goal, to have an impact. So that's great. Good luck with generating huge impact.
Okay.
Yes.
Thank you. Pleasure.
Thank you very much.